Hello. I would like to start by thanking the organizers, particularly Declan King, for giving me this opportunity to present some of the recent research findings from our group and which are being commercialized through our spin-out company, Aston Particle Technologies. The presentation today is titled Thin Layer Fluidisation, a new paradigm for formulation of DPI. Over the course of the next 15 to 20 minutes, what I will be looking at is starting my presentation with a brief background on the challenges in the formulation of DPIs. This have split into challenges presented by the API and the existing processes used in the formulation of DPIs. And then that hopefully should sort of give us some scene setting in terms of whether there is a need to innovate and look at new processes. And that should then lead us into thin layer fluidization, which is the core topic for discussion today. And the concept of thin layer fluidization, I've split that into two key areas. One is to understand the mechanistic aspect of how this works and what are the underpinning principles. And then the second part is pretty much like a case study, formulation of high dose blends. We're looking at typically 15 to 25% weight over weight API and beyond. And then a summary trying to bring together the key or the salient features of thin layer fluidization. So when we look at the formulation of DPIs, the API itself presents some significant challenges. The physical and chemical instability. For example, we know that inhaled drugs are extremely cohesive because of the small particle size, and coupled with that, if the material itself is sensitive to heat or sensitive to solvents or moisture, then that again presents another layer of difficulty. Similarly, dose, where we have to deliver very concentrated formulations where the API exceeds the monolayer coverage of the carrier, then that is a significant issue. And scale up basically sits between API challenges and process. And within, for this particular area, we need extensive optimization to scale up from R&D batches to manufacturing scale batches. So when we look at the process-related challenges, the most common industrial method for formulation of DPI is high shear blending. Now, the challenge presented by high shear blending is that because of the setup of the equipment itself, where we have a fixed vessel with a rotating shaft and paddles coming off that rotating shaft, this arrangement leads to different mechanisms of blending within the same processing vessel. So for example, particles which are close to the central shaft experience high velocity, and therefore the primary mechanism of blending is convection and diffusion. On the other hand, particles which are close to the periphery experience higher velocities compared to the ones in the central region, and they are subjected to shear. And the consequence of this difference in velocity is that the particles that are close to the periphery undergo or suffer attrition and result in new surfaces, whereas the ones that are close to the shaft generate surface charge and lead to triboelectrification. So, with these sort of some of challenges in mind, is there scope for new modalities in powder blending? Because when we look at the various methods or various techniques available for mixing, whether it's high shear blenders or tubular mixers or any other technology, the primary driver in these different technologies is the solid movement of particles. So we then thought, could fluidization, in particular thin layer fluidization, overcome current limitations? Does it offer any advantage over existing methods? Does it provide any major benefits compared to the existing methods of blending? That then led to the discovery of isothermal dry particle coating. Now, isothermal dry particle coating is based on thin layer fluidization. So IDPC uses a fast rotating chamber and nitrogen gas to blend and layer powders in a process called thin layer fluidization. So what tends to happen is, when you have a very small cohesive particles and you want to blend them with large carrier particles, with the controlled injection of nitrogen into the processing vessel, and the vessel itself actually rotates at a high G-force, that leads to deaggregation of fine particles and subsequent deposition of these deaggregated particles onto the carrier particles. The key here is that this process occurs at ambient temperature and does not require any additional facilitators. And it's not based on solid movement of particles. The presence of the thin, or the presence of the dry nitrogen facilitates the introduction of thin layer, i.e. it's a thin air curtain of nitrogen that fluidizes the powder as a very thin layer, and that coupled with the high centrifugal force can promote, or that leads to deaggregation of fine material and its deposition onto the coarse particles. What are the different steps? In here, in the case of thin layer fluidization, if we sort of dissect this process and try and understand what happens at each stage, albeit it doesn't happen as sequentially as represented here, but for our understanding, we've decided to sort of split this into three key steps. The introduction of high or the introduction of high centrifugal forces through the rotation of the drum causes the powders, both fine and coarse particles, to stick to the periphery of the rotating drum. Then the introduction of the thin layer or controlled nitrogen allows the formation of the thin layer. So introduction of nitrogen gas within the processing vessel fluidizes this material, and this nitrogen gas acts like an air blade or an air curtain. And this fluidization is not an extensive fluidization as you would see in a fluid bed coater, for example, in granulation or tableting, but this is a very, very thin layer. And this leads to de-agglomeration of very fine particles. And when these fine particles are de-agglomerated, because of the high surface energetics, these particles then tend to layer themselves onto the surface of coarser particles which have relatively lower surface energy. And this process of adsorption then leads to the coating of particles. We can generate discrete coating or continuous coating or multiple layers of coating, but the key here is that all the fine particles are de-agglomerated and adsorbed onto the surface of the carrier particles. Is there any further evidence? Yes, because thin layer fluidization, there are three critical parameters: the centrifugal force as a result of the rotation of the drum, the flow rate of the nitrogen, and the duration of processing. So when you optimize or tweak these three process parameters, then you can generate particles with different degree of coating, different degree of aerosolization. For instance, here are confocal images where we've taken micronized rhodamine and coated it onto lactose, inhalation grade lactose, and this was done at 201 G for 20 minutes at different flow rates of nitrogen. And what you can see here is that the particles of rhodamine are uniformly coated onto the surface of the lactose. And what we then did was we used the fluorescent intensities to actually map how these particles of rhodamine which fluoresce, how the intensity changes during the duration of the processing time. And what we were able to see is, for instance, if we take one of these, let's say 25 liters per minute, flow rate of nitrogen, what you see is at the start the fluorescence intensity goes up, whereby we think at this stage the particles are beginning to de-agglomerate, and as a result of this de-agglomeration phase you get individual particles, and this then over the course of the processing time leads to dispersion and uniform coating of the fine material. Now the similar trends were observed when we changed the flow rate of nitrogen. So basically the three key steps that we hypothesized at the start, i.e. de-agglomeration, dispersion and coating, we were able to not only confirm that through qualitative imaging, but also through quantitative measurements of fluorescence intensity using a confocal. This mechanistic aspect was also studied by using SEM. For instance, these are SEM images of blends from an innovative product, and the same formulation when prepared using thin layer fluidization. Well, there are a couple of key observations here. In the field of view, you don't see any agglomerates as you would see in the innovative product, and when you take a closer look, each of the individual particles of the API is fully de-agglomerated. So having sort of gone through the concept the mechanistic aspect of thin layer fluidization, the question would be, okay, in addition to some of the obvious advantages of thin layer fluidization, does this technique have any application in the delivery of high dose compounds? Because with high dose, it gets very tricky, because if you're exceeding the monolayer coverage, then it's not just a case of managing the interaction between the API and the carrier particles, but also the interaction of the the API particles themselves. So as soon as you start to look at coverage exceeding the monolayer, then how the particles arrange themselves, i.e. the API particles, how they arrange themselves, and what does that mean in terms of aerosolization? That's a key challenge there. So the question we have to ask ourselves is, does the same principle that we've just discussed earlier, does that also apply to high dose blends or not? So we looked at fluticasone propionate as a model compound. We studied a range of different concentrations, starting from 0.7% all the way to 25%. In fact, we've done work with 50 to 70% API, but I'm only presenting here data for up to 25%. So there's an interesting trend here. So irrespective of the percentage concentration of the API, what you can see is that the NGI aerodynamic particle size distribution, for instance, here is showing some very interesting trends. As concentration increases up to 25% weight over weight, you can see more and more fluticasone propionate is deposited in the lower stages of NGI. Again, this is quite evident when we look at the MMAD. So this, what this data is suggesting is, as you increase the concentration, you get a finer dispersion and therefore a drop in MMAD. Similarly, another conclusion that can be drawn from here is that there is no agglomerates, i.e. the particles of the API themselves, it can be assumed that they are now fully de-agglomerated, completely dispersed. So as a result, the key challenge in delivering high dose compounds, i.e. the cohesive forces between the particles themselves, especially where after you've exceeded the monolayer coverage, that basically can be overcome using thin layer fluidization. Then the next question is, okay, what could be the reason, or how could this be happening? So we did some SEM imaging. For instance, with 5% weight over weight fluticasone, what we see is particles nearing full surface coverage. So again, in the field of view, you can see all individual particles of the API being coated onto the surface of the carrier. Now, when we go to 25% weight over weight FP, we have an interesting arrangement here. The API particles, they form a very porous structure. Now, the porous structure, the way it's arranged is the best description of this is like a house of cards type of structure. Now, what this does is it gives us a good balance between coating the API onto the carrier, and at the same time ensuring sufficient aerosolization, as we've seen with the NGI data in the previous slide. So it's how these particles are arranged, and this specific arrangement gives rise to specific advantages in terms of both coating and aerosolization. So in summary, the thin layer fluidization, which is part of, or which is based on isothermal dry particle coating technology, can be used to deliver a range of different APIs. No pre or post processing of materials required, i.e. you just use off-the-shelf materials, generates high content, tight content uniformity, and most importantly, you can dial fine particle fraction without changing the composition of the formulation itself. It's a very scalable process. We've got data with using long-term stability studies, where we've got formulations which are stable up to at least 18 months. This technology can be used to formulate fixed dose combinations, lends itself very well to quality by design, because we go very specific, or we've got a very simple 3 different sets of critical process parameters. So quality by design it can easily be applied in the formulation development. So using IDPC. So in conclusion, is there a scope for new modalities in pattern blending? I hope I have convinced you that there is. So isothermal dry particle coating, which is based on thin layer fluidization, gives you an added advantage where you have a better control on the formula blending process, where you can use high dose compounds, and most importantly, where you get reproducible results which can easily be scaled up. So I want to conclude my presentation thanking my PhD student, Olaita Nabiona, as well as my colleagues at Aston Particle Technologies, which is commercializing this thin layer fluidization technology, and in particular Dr. Justin Kona and Professor David Wyeth. I'll be more than happy to take any questions, and if you want to get in touch with me, my email is on the opening slide. Thank you very much.